Hi everyone, hope you're having a great day today. We're going to go over section 11.6, which is polar equations and graph. So we're going to look at how to graph polar equations today, and we're going to compare and contrast the difference between polar equations and Cartesian coordinates and in the polar coordinates. So in the polar system, what we have is a point called the pole, and I'll compare and contrast the difference between this so that you kind of see the similarity. Polar versus Cartesian. So in polar coordinate, we call the pole, but in the Cartesian coordinate, we just call that the origin. And they're the same point, essentially. So the polar axis is over in the Cartesian, we call that the positive x-axis. Okay, so it's only going to go to the right. And what we're going to do is we're going to rotate this polar axis counterclockwise, just like how we normally rotate an angle, in order to find out a point that is our distance away from the pole. So in order for us to identify a point, we use the order pair r and theta, similar to x and y. Okay, so let's look at how we achieve a point in the Cartesian coordinates. In the Cartesian coordinates, we go x amount, so we basically go horizontally x amount, and then we go vertically a y amount. So this point right here will give us x and y. Okay. Now in the polar coordinate, we have r, which is the distance from the pole to that point. So let's say this is the same x, y value as over here. Now the r would be the distance from here to this point xy, and the angle theta is the rotation from the positive x-axis or the polar axis, rotate. So basically we have a ray that we rotate along this pole in order to get our point xy. So we achieve the same thing, it's just a different method on how to do that. You will see the benefit of polar equation in a second. So how do we convert from one form to another? Well, if a point have a rectangular coordinate xy and a polar coordinate r theta, let's see how we achieve the same thing here. So let's say we have this point xy. We know that we achieve the horizontal as x and the vertical as y. Now, if I use the Pythagorean theorem, I can just get r. So that's just x squared plus y squared. And then take square root of that. That's just Pythagorean theorem. Now, I can find out this angle theta because that's just tangent using opposite over adjacent. So tangent theta is equals to y over x. That's how I got this here. And of course, x equals r cosine theta and y equals r sine theta came from our coordinate system when we were learning about the unit circle. Xy is equals to cosine theta and sine theta. Now, since we are talking about the unit circle here, we did not deal with r, but here this is in general. So r is just a scalar value that will extend this ray to whatever length that we need. So we no longer have to deal with just unit circle. We can talk about any circle with radius r. So let's look at how we plot these. We're going to plot each point by hand in the polar coordinate, then determine the rectangular coordinate of each point. Okay, so let's look. So for part A, I'll do the first one, and then each one of you will do the other one. So we have a point 30 degrees. Okay, so my r value is 2, and my theta is 30. So first, I'm going to draw the angle first. So figure out where that angle is. So here, let's say that this is 30 degrees. And then you can figure out your length, which is 2. So we can call this length right here 2. So since I have r and I have theta, I can figure out what is my x and my y is equal to. We can see here this is in the first quadrant, so we know that x and y will both be positive. And remember that x is equal to r cosine theta, and y is equal to r sine theta. So I can plug it in. R here is 2 cosine of 30 degree, 2 sine of 30 degree. So cosine of 30 degree is square root of 3 over 2 times 2, which gives me square root of 3. Sine of 30 degree is 1/2, so we just get 1. The y value is 1, x is square root of 3. This makes sense because this is a 30-60 degree triangle. We have 1, 2, square root of 3. That is a triplet for the special triangle. Okay, so let's look at part B. So over here, if r is negative, here we have an r that's negative, it will point in the opposite direction. So let's draw -4 and 2/3 normally. So first I'm going to draw 4 and 2 pi over 3. So you can have an idea of what that looks like. So 2 pi over 3 is in the second quadrant. That's basically about 120 degree. So from here to here is 2 pi over 3. Now the distance right here, if it's positive, is going to go here. So my point would be here. 4, 2 pi over 3 would be here. However, this r is negative. So that means we're going to take this and go in the opposite direction to be down here. So my r is still the same. However, my angle will change. So my angle will now be from here all the way to here. Okay. So if I give you -4, 2 pi over 3, the point would be here. Now, of course, you can find out another way to write this angle by using a positive r. If you find out what is this angle equal to. Well, if this is 2 pi over 3, our reference angle here is pi over 3. That means that this here is also pi over 3, but it's negative, right? So that means that in the positive direction, this is 5 pi over 3. So you have many different ways of writing the same point, just like an angle. So let's look at all the different ways that this is equal to.
Hey,
We
Professor.
have -4, 2 pi over 3. That is the same thing as if I use a positive r and I use this angle, 5 pi over 3. Or I can use a negative angle and a positive r, negative pi over 3. So you can see here I have all different kind of combination, right? So I can even go one better. I can want both of them to be negative. You see here I have a different combination, both positive. One of them is positive. Now, what if I want both of them to be negative? Okay, if I want both of them to be negative, that means I want here to rotate in this direction, and then my r is going to be negative. Okay, so this is 3 pi over 3. This is 4 pi over 3. So I want -4 pi over 3. And my r will be -4. All of these here will equals this. Okay, does that make sense? Any questions?
I'm sorry, can you go over where we got that last one where both of them are negative, the -4 pi over 3? Could you use
Sure.
one other color, please?
Sure.
Or
I'll
is it
redraw the whole.
yeah. And I mean, what's the reasoning of trying to find different variations of the same polar coordinates there? Is it just because we can solve it analytically in different methods?
Yeah. So you just so you know that all different combinations are possible.
Okay.
Okay. So if you got one out of the 4, you can always convert it to being it both positive. Okay, so normally this is what we want. That's a standard for. Okay. All right, so let's look at how we achieve the value. So this is our point, right? This is our point Q. We want to get here. In order to go here, the requirement is I want both of them to be negative. Well, if I go in the opposite direction, which is my angle, going this direction, that's a negative angle, right? But that's negative 4 pi over 3. Now, being a positive 4 will end up here. But since it's a negative 4, it's going to flip in the opposite direction and go here. So this is my final point here.
Okay. And then when we write in the polar coordinate, regardless of the sign of the r value within the bracket, the length of the vector, the magnitude of the vector is always positive, right?
Yes. Direction. That does not tell you that you have negative magnitude. That's not possible. That make sense?
Yes.
All right, moving on. Okay, so I want you to find the following variations. Okay, so I want you to find r is positive and theta is positive. R is negative and theta is positive. R is negative. What's the other combination?
The initial one, right? Positive and negative.
R positive, negative. And this one's already right there, so we don't need to do this one. Mai, you can do C on the whiteboard, and Aim, you can do B.
Hey, Professor, you cut off. I know Mai's doing C. Which one am I doing?
B.
B it is. Thank you.
And when you're done with that, convert it to rectangular coordinates. Emma, you done?
I'm still converting to rectangular coordinates.
Yep.
Okay, I think I'm done.
Okay. What you get for x and y?
For x, I got 5 root 2 over 2. And for y, I got negative 5 root 2 over 2.
Very good. How'd you get the same thing? All right, let's move on. And you can see here, 5 squared over 2 over 2 and negative 5 squared over 2 over 2 because we're in the fourth quadrant. Okay, so now we're going to see give 3 other pairs of polar coordinates for the point P3 and 140. So that's exactly what I've been showing you. So here is one of them. Now find the other 3 combinations that deal with this. So make R positive, make theta negative, positive, and then make both of them negative. You can do it on the side there. All right, so you see that we have 3, negative 220 for the first one. So let's look at how we get these values here. So 3 and 140 will set us over here. And this point right here, let's say this is 3. So we can go in the opposite direction. That would be a negative theta, and that's going to be negative 220 degree. So we can have negative 220 degree and a positive 3. So that would give us the first one here. And of course, we can also go in the opposite direction. This will give us a negative 3 if we go over on this direction. So you can figure out what is our reference angle from here to here is. And that's going to be 40 degree. So that means that this is 40 degree. Okay. So if we go negative 40 degree and negative 3, that would give us this solution here. Of course, we can now go negative 3, but rotate this direction. okay, which is 320 degree, and that would give us this solution here. All right, for part B, -1 and 1. -1 and 1 is in quadrant 2, and all you have to do to find r is use a formula. So to convert from rectangular to polar is actually a lot easier, because you can just plug into the formula. So r here is square root of x squared plus y squared, and theta you can use tangent, which is just tangent of 1 over -1, which is -1. And so tangent of -1, that's basically the reference back to the first quadrant is 45 degree. Since it is in the second quadrant, you can subtract that in order to get the values 135.
Professor, I'm sorry, I don't understand why we calculated the r to get square root of 2.
Why it's square root of 2?
No, not why, but why we did that. Like, why are we? I mean, I understand why we got theta from tangent. That's clear to me. But why did we solve for r?
Because we're trying to put it in polar form, which is r theta.
Oh, okay, okay.
Yeah.
Okay,
So we
and
need
then
to find r.
got it. And then the -225 is just the negative coterminal of 135.
Yes,
Okay, I see what it did.
exactly. Let's go this direction, whereas this go this direction. All right, so now we're going to look at an equation. So for each rectangular equation, give its equivalent polar equation in Sketch's graph. So for this, you will need to refresh how to complete the square on some of them. So let's look at y and x here. So for these, you can do the direct substitution, where x is equals r cosine theta and y is equals r sine theta. We do that, and then we just substitute it in and solve for r. So in rectangular coordinates, this is our y-intercept, and the slope is 1. Right? So remember, y equals mx plus b. So you can see here, my y-intercept is at -3, and of course I go up 1 over 1, up 1 over 1. So you can see here my slope is +1. Now when we can convert it, we do the direct substitution. X is r cosine theta, y is r sine theta. Factor out an r, both of them, and then divide both sides to solve for r. So this is our equation of this. So you can see here, this is not very pretty, right? So polar coordinate system is not really used for lines. Let's write that here. Okay. Polar coordinate is not great at graphing lines. It excel in sketching curves. That's the majority, and that's the reason why we use polar coordinate, because it involves theta, and theta help us sketch curves. So let's look at the second example. X squared plus y squared equals 4. Do you know what this shape is?
That's a circle.
That's a circle, right? That is a circle with radius of 2. So the equation for a circle is x squared plus y squared equals r squared. That looks kind of familiar, right? That's basically how we solve for Pythagorean theorem. So here the radius is 2. And all this does is, you notice, if I substitute x squared in, I get cosine theta squared plus sine squared theta is equals to 4. That looks similar, right? Because that looks very much like the identity cosine squared plus sine squared equals to 1. Now, all this right here, this is for 2, and so equation is in terms of r. Basically, r equals to 1. Now, I know that r is x squared plus y squared, so this entire thing here is equals to r. r squared. So therefore, when I try to solve for r is equals to plus or minus 2. Now you notice in this equation, there is no theta. Okay. So theta is a free variable. So what does it mean by a free variable? Free variable means it's free Okay, so there is no restriction for what theta can be. So basically from 0 to 360. And you can see here that r equals to 2 is a point 2 spaces away from the pole. And you can see here that gives us essentially a circle. Because all these points here are 2 units away from the pole. And you can see here, since theta is a free variable, it's free to be whatever you want it. So therefore, you can rotate that all the way around 360 degrees. Give us a circle. Does that make sense?
Yes.
Okay, great. Any question, Mai, Soraya?
No.
Okay. All right, so now we're going to get to a little bit more complicated equations.
I
Okay?
have a quick question, sir. Are free variables only applicable to circles, or can they be applied to? I mean, obviously they can be applied to sinusoidal waves and cosine waves because they're a function of a circle, right? But are there
Yeah.
any other applications to a free variable?
Mm-hmm. In linear algebra.
Okay, thank you. You piqued my interest.
In linear algebra and also in matrices, there's a lot of that too.
Would a free variable be analogous to a scalar somehow?
No.
Okay.
A scalar is something you multiply with to change the magnitude of it, but this is not. This does well. Okay, here is something that you think it may be like a scalar value is when when theta is equal to let's say pi over 4. So you see here in this equation, the free variable is r because you don't see an r in this equation, right? So what do you think this graph is in polar coordinate?
It's r comma pi over 4.
Hold on, let me add. See if I can copy this over here. I wonder if I can paste this in here. Oh, yay. Awesome. There you go. All right, so this is the coordinate, polar coordinate system. And this is how you can graph whatever shape in polar coordinate. So theta is equals to pi over 4. Now, pi over 4 is 45 degrees, right? So that means that you have this here. Now, I told you that r is a free variable, so r can be whatever you want. It can be -2, -1, 0, 1, 2, dot, 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 dot. So it can go to negative infinity and positive infinity. So now with that hint, what do you think this graph is?
My intuition says that that graph is all cases where the vector or the line occurs at coterminals of at multiples of 45 degrees. So 45, 135, 1.
Yeah. Times theta.
Okay.
That's not true.
Okay.
Okay, so think of it as that's point. So what if I tell you to graph the point 0, pi over 4? What if I asked you to graph the point 1 pi over 4, 2 pi over 4, and so forth? Now, this is similar to graphing x equals a number or y equals a number. So if I have, for example, y equals 2, what is the shape of this line?
The shape of that line is just a straight horizontal line at the y equals 2 mark.
Yeah, so the y-intercept here is 2. Shape of x equals to 2.
It's going to be a vertical line at the x equals 2 point.
Right. Now, that's a vertical line. This is a horizontal line. Now, what is the x value for this graph?
0.
Yeah, it can be 0. It can be 1, 2, 2, 2, 3, 2, and so forth, right? But the same thing that's in common is all the y value is 2, right? Now over here, similarly, all the x value is 2. So 2, 1, 2, 2, 2, 3, 2, 4, whatever, right? So the x value is the one that's fixed here, okay? This is your free variable. It's free to be whatever number you want it to be. X is not a free variable. It has to stay fixed at 2. Okay, so over here, x is my free variable. Okay, so think of that. Now, when you go here, you have r and theta. Okay, r and theta. Theta is your fixed variable. It does not change. Whatever value we want it to be. It could be positive, it could be negative, it could be 0, it could be whatever.
Okay.
So if I
so
plot r1, give you this point, r3 gives you this point, and so forth. If I go negative 1 pi over 4, it gives me this point, this point, this point, and basically all the points in between, because it can be whatever value, right? That gives me what?
theta equals pi over 4.
That gives you a line
Okay, yeah.
going through pi over 4. So theta equals a number is a line going through the pole. Okay, the pole here is like the origin. Okay, so you can rotate this around this pole to be any angle you want, but you're still going to get a line if it's theta equals to a value. Okay, that makes sense?
Yes, I get it.
So yeah, so if I say theta equals pi over 4, that's actually the same equation as theta equals to 225 degrees. Because you notice here they're the same thing. Okay, they're 180 degrees from each other. But since r can be positive or negative, it doesn't matter. Okay, so these two are the same thing. Same line. Yeah, I hope that helps.
They are coterminal angles, pi over 4 and 225.
I'm sorry, say that again.
Yeah, I mean they are just coterminal angle. They have the same sign and the same cosine.
I don't want to say they're coterminal because when you're talking about coterminal angle, that's different from this. These two are equation of a line in polar form. Yeah, they are not an angle per se, so you cannot say they are coterminal. They are not coterminal.
Oh yeah, yeah.
They are equation that give you the same line, but coterminal means they end on the same
Angle. Yeah.
yeah. This is not. Yeah, one of them is 45, one of them is 225. They're not coterminal. Okay, so now let's talk about something a little bit more interesting, and we're gonna investigate in r equals 3 sine theta and r equals 2 plus cosine theta or r plus sine theta, and we're going to look at the form and we're going to look at what will changes as we change the value of this and we change the value of theta. Something's going to happen, and then we're going to summarize all of that into a nice little chart that you can help to memorize what's going on when we change these values. So we're going to play around with it, and I want you guys to see if we can use ClassCalc in order to do this, or if you have a graphing calculator, that would be good too. Okay, so I'm still unfamiliar with ClassCalc and with using polar coordinates and stuff. So, all right, so let's go to this first, and then ClassCalc. Oh, I got it. Never mind. Okay, so we're going to graph 1 plus cosine theta. Okay, so remember this is polar coordinate, so we need an r and we need a theta. Now theta is going to move from 0 to 360 degrees. Okay, and it's going to go counterclockwise. Okay, and you can see here theta, 0, 30, 60, 90. We all know these values, right? So let's see what happened as we rotate on the positive x-axis. So here, this is where we're going to start out. And we're going to rotate this direction, okay? Then the r is what's going to change as theta is moving counterclockwise, okay? So let's look what happened. When cosine is 0, we get 1. 1 plus 1 is 2. So this distance away from the pole, okay, at 0. As I increase, we'll see all these values get smaller and smaller and smaller until it's going to approach 0 at 180 degrees. Because theta at 180 degrees is equal to what? Cosine of theta is equal to what? Cosine of 180 degrees.
-1.
-1. So we have 1 plus -1 that equals to 0. Equal to 0. So you'll see this rotate around here, and then as it gets closer and closer to 180, it becomes 0. Now I'm going to show you this on the calculator, and I'm actually going to use the graphing calculator because I want you to see the path that it takes. So if you have a graphing calculator, feel free to uh-oh. Okay, so first thing first, we need to select our mode. So the mode is going to be either in radian or degree. Let's use radian. Actually, no, let's keep it at degree. That's fine. So you can see it a little bit better. And then we're going to select polar for our function. And everything else you can kind of leave. If you don't have all these options, that's okay. It just means you have an older calculator that you haven't updated yet. All right, so now let's go to y equal. Now what I want you to do is to select this right here and make sure that you have a dash and a circle. Okay, this is going to show you the path that the point is going to take as theta moves from 0 to 360. Okay, so we're going to type in 1 plus cosine theta. Now, before you press enter, we need to go to window, and we need to check these values. So the default is by radian. And you can see here is at 2 pi. So we need to change that to 360 degree because we are using degree. Now the step here means that how often does it calculate? Well, let's do it by 1 degree at a time. So every degree is going to show you a step. So it's going to calculate theta equals 1 degree, 2 degree, 3 degree, and then it's going to plot those points. And then it's going to show you what the graph looks like. Now, if your step is too large, you're going to see very jagged edge. And I'm going to show you this later in a second. So x min, x max here. We probably should put this to, let's do 2, negative 2. We're going to square this off in a second. Same thing for y. Okay. So before I do that, I'm going to hit zoom, and I want to use zoom square. This is going to square up my screen so you have a better sense of the scale rather than it being squished, because your screen is a rectangle, not a square. This will square it up for you. So look carefully on the path that this takes. You see the circle? As it's moving around theta from 0 to 360 degrees. So this right here is when it's at 180 degrees and continue to be in the third quadrant, and then moving on to give you a full circle. And that's it. Okay, so if you set your theta to be larger than 360, it's just going to follow the same path again. Okay, any question?
Did you ever figure out how to do this in class calc?
Yes. So okay, so I can show you that on here. Let me move to the other screen here. Okay, so you're gonna have this, pull this up, and then hit graph. You're gonna type it over here, cosine, and then to add theta, you just type in theta, and then it'll convert it automatically for you. So the only downside here, the path that it takes, okay, and that's it.
So if theta is positive, do we always assume a counterclockwise movement?
Yes.
Okay. And then do clockwise movement exist if theta is negative? Or is that something outside the realm of the range or domain or something like that?
The clockwise what? Say again.
So if instead of cosine theta, if it was cosine negative theta, would that mean a clockwise movement on the path?
Oh, that's a great question. Let's see what happened. In a second. All right, so let me go back and answer your question first. Always the inquisitive one, huh? Oh man. Stupid board's acting up again. And it just turned off everything.
Is this your writing tablet? Your drawing tablet?
Yeah,
Oof.
should probably return this.
Yeah, that Amazon Prime free return stuff.
Yeah. Yeah. This is my second one. I've already returned the first one. Still messing up. Okay, so to answer your question, what happened when cosine theta is negative? So we have, let's see, was R equals to, I'm writing with my mouse now, so it's not going to be as pretty. Okay, so what happened if you have R equals to 1 plus cosine of negative theta? Now we're going to use an even and odd property. Cosine of negative theta, and since cosine is an even function, this equals to cosine of theta. So nothing changes. It's the same thing.
That's very cool. Thank you.
Did that answer your question? Yeah.
Yes.
Okay, so let's continue. Okay, so we're going to look at different scenario where we change R and theta. So at least I don't really need to use my anymore. So let's go back and look at your graphing calculator. Does all of you have a graphing calculator?
I
Yes,
do,
I
yes.
have.
Good. Maya, do you have one? I can't hear you, Maya. But yeah. You can just type in the chat. Yes or no. Okay, so I'm going to see if you guys can figure out if there is a pattern. Okay, so I'm going to point out certain things to you first. Okay, so let's look. This is 1. Okay, this is positive theta, so nothing too complicated yet, right? So the value in front of this cosine is also 1, right? I'm going to change some numbers around and see if you can notice the difference between the graph. So I'll leave the blue one there. I'm going to change the red one. So I'm going to say 2 plus cosine theta. Then I need you to identify what is the difference between the two. Okay? And then you're going to figure out if there's a pattern to this. All right. What do we see? Not obvious yet? What about, we're saying?
I was going to say if the R was increased, so in this case it was doubled, the circle is larger, and then as it decreases to its minimal point, it doesn't get to 0. It gets to 1. I was going to, looks like it's 1 or 0.5.
Oh, look at that. Let's look at the third one where I change out the 1 and the 2. 1. All right. So what is the difference here? Maybe I should zoom out a little bit.
Professor, what was the
Too
equation for the third one?
much. Hold on. Let me stop this here. Maybe let's do -4 and 4. And I just changed the order, 1 and 2. And then the next one I'll do 2 and 2, so you can see the difference. All right, here we go. Here's the first one. This is the regular one, 1 plus cosine theta.
It looks like an egg, sir, like a soft-boiled egg.
Well, the reason why it looks like that is because it's not square yet. So that's the reason why I told you guys that anytime that you are trying to use this graphing calculator, you need to hit zooms square right here, because everything's going to look squished if you don't. So now the X and Y tick marks are actually the same scale. So you can see here, right? The same distance from here to here is the same as distance from here to here. So they are all on the same scale. Actually, this is too slow, so let me do it a little bit faster here. Let's do change the step to 2, so it goes a little bit faster. There you go. All right, so now you can kind of see it's a little bit better. It's not being so squished anymore, right? So you're not going to think it's like a football or an egg or something. So let's look at the first one, right? The first one was the blue one. That's 1 plus cosine. The second one was this value is greater than this. So you see what happened here. Kind of bulges out. And then the third value, I flip it around, so 1 plus 2 cosine theta. And now it creates this little circle in here. And so what can you conclude here? And you notice all three of them kind of have the same distance here at 3, 0. So I'm going to...
I was going to ask, is there some kind of periodicity when you added the 2 cosine theta? So when you increase the cosine theta by an amount, by a scalar amount, like 1, 2, 3, 4, does it increase like a period, or does it add more periods into it, which allows it
No,
to...
that does not add period. No.
Okay.
That changes the R value. Okay. So now let's go back to the whiteboard and let's look at some form. Okay, so the form that I want you to consider is this. A plus B cosine theta. Okay. All right. If A is equals to B, what do we have? What kind of shape do we have?
We have the shape that we initially saw in the first equation, where
Yes.
it starts at the
Shape.
maximum, yeah, and then it goes towards a minimum of 0.
We call that a cardioid. So a cardioid is basically a shape that looks like a heart. So you can see here that's kind of look like a heart right here, right? Okay. We call that a cardioid. Now, it gets a little bit more complicated when A and B are not the same. If B is greater than A, what we have is called a limousin. It's French. Lemonets. Okay. You're gonna see this word later on, so if you can't read that, I'll show you later on. If B is greater than A, is a limousin with a loop. Okay, so that's the one where you see it goes like this, then it's gonna rotate, and then that. So this inside loop right here. Now the distance between that loop is actually very specific as well. So let's go back to the calculator and see if you can figure out different type of limousin and see if you can see a pattern. So in this example, I'm going to show you 3 different. You tell me what is the difference between them. So I'm only going to change the and see if you see there is a pattern that occur when I change them. Okay, so the first one is 2, 3, and then 4.
Is the distance from the inner loop, from the origin to the inner loop, half of the R value?
You can't say R value. So what I'm going to give you is the A and the B value. In the B value.
So if that was. Oh, okay. So. I mean, is it direct? The distance. The distance of the inner loop is just the difference of the A and B value then.
Very good. There we go. So let's look at the first one. So I'm going to remove these two. I looked at the A and the B value, right? So the A is 1, the B is 2. All right. So the distance from the pole to the longest or the furthest point is 3. Well, that's not a coincidence. That's equals to A plus B. The distance of the loop, which is 1, that's not a coincidence. That is actually equals to B minus A. The distance of this right here, where the quote-unquote y-intercept is 1. That is equals to A. Now, if I change that to 2 or 3, let's see what happens. I hope you're writing this down. I'll review everything here. Okay. All right, so let's review again. The distance from the pole to the furthest point is A plus B. So from here to here is 2 plus 3, so you get 5. The distance of the loop is B minus A. So 3 minus 2 is 1. So the distance of loop is 1. The y-intercept here is equals to A, which is 2. So you see positive 2, negative 2. And that's the critical values that you will use in order to sketch any of these.
I'm sorry, Professor. We went a little faster. I got the A plus B. I got the B minus A. I
I'll
got.
write it over here.
Okay.
I'll write it again in the whiteboard. I'm going to plug in my tablet. Hopefully it doesn't close out everything again.
Professor, I have a little problem with my calculator still. It show me you have an error with Windows. Can you show again the window? What should I do with it?
Oh, sure. So if you go to your window, you have to make sure, since we're using degree, it's 0 to 360, and then your x min and x max here is whatever they choose it to be when you are squaring in your screen. So you can just put -4 and 4, and then when you go to zoom, hit zoom square, and then we'll select the screen for you.
Okay, just I have a little this problem. I plug it in my calculator. X minimum is -6.4.
Yeah, so this is the calculator calculating this for you. But you can just put in -6 and +6. That's okay.
Okay.
For
Okay.
y min and y max, you can put -4 and 4.
-6.
And then when you go to hit zoom, hit zoom square.
Okay, -4 and 4. And the zoom means
Zoom square.
is number 5? Okay.
Yeah, number 5.
Oh.
And then you will have the graph. Yeah. Any
why I still have error? Maybe
you go to mode, make sure you do in degree. Degree and polar. If you still have a problem, go back to y equal and see if you type in anything wrong here.
My mode is on degree pole. That's
Yes,
right.
degree and polar.
Yes, it's the same.
Go back to y equal and see if you type this in correctly. If it's still giving you an error, do you see any of this plot right here highlighted?
Yeah, I just
Yeah, if any of these are highlighted, you need to unhighlight it. So go back up here.
highlight that one.
That's going to unhighlight it. So that's probably why, because your plot is on.
Doesn't work. I tried after the class. Maybe
It still doesn't work?
mine is not still. It's just
What kind of error does it say?
Something
What kind of error does it
say?
This window error?
Window in ERR window range.
Oh, that's in here. Wrong. Can you double check?
Okay. X minimum -6.4.
Oh. 6. You'll be using the minus sign. Don't use the minus sign. Use this sign down here. This right here. The one that is next to the enter button. Don't use the minus.
I use this one. The inside the parenthesis. I use.
Yeah. Number and -4 and 4.
1 minute.
And then your I think your theta is probably what's messing it up.
1. I don't know decimal.
But you don't have to type in these decimal. Just type in -6 and 6.
I plug it all of this number.
But you don't have to type in the whole numbers for x min and max. Okay, how about this? Let's forget all this and just hit zoom standard. Go down here and hit zoom 6. We'll go to the standard size.
Zoom 6.
Yeah. Does it work now?
Now I see. Okay, thank you. It's working now.
It's working? Okay, yeah. It's something to do with this right here. You're typing something in wrong here. But after you do zoom 6, now go back and do zoom 5. Zoom square.
Okay.
Yeah, so yours should look a little bit smaller than this because your zoom standard, which is 10 by 10. Okay, so let's go back and
Thank you.
you're welcome. Okay, so let's go back. Let's see. All right, so let's look at A and B here. All right, so if B is greater than A, we have Levinson with loop of size B minus A. So the loop is equals to B minus A. So your A value is like your y-intercept. A plus B is basically your max R value. You can also think of this as like the tip of the cardioid. Okay, so we got A, we got B minus A, we got A plus B. So let's see if I can try to sketch this. Oh, that's actually not bad. Okay, so the distance from here to here, that is B plus A or A plus B. The distance from here to here is B minus A. And the distance from here to here is A. Same thing, here to here is A. All right, there you go. So these are the reference points that we're going to use. See, we have 5 reference points here to use in order to sketch this. Okay?
Okay.
All right, so let's see what happened when I change it to sine. So let's guess what happened if I have R is equals to 1 plus sine theta. And then let's see what happened when I have R equals 1 minus sine theta. Okay, can you guess what will happen?
Is there some kind of rotation involved?
Mm-hmm.
Is it
Now,
like a? Oh, go ahead.
now remember that sine and cosine only differ by 90 degrees. So yes, you can definitely think of that as a rotation of 90 degrees. But rotation which way? So here you see the tip of it is being pointing in the positive x direction. Now remember that sine of 0 is 0. Okay, so you're going to start out 1. However, as you rotate, where is the tip going to be? Okay, so you can use your graphing calculator to see the direction that the value is moving, to see where the shape is. Okay, so let's go back to our calculator. So let's see. Oops, that's not calculator. Okay, so let's try 1 plus sine theta. Then in a second, we'll look at 1 minus sine theta to see what it is, and then write down the difference. Okay, so you see here, it does start at 1, right? Then keep going. There you go. It's going to make a cardioid with the tip of the cardioid pointing up instead of going to the right. Now, what happened if I do 1 minus sine theta? Anyone guess?
I want to say that the tip's gonna be in -1, or it's gonna be in the negative y-axis.
So different.
It's going to be a
Or would that be a
cardioid.
rotation? What?
I think it's going to be the same cardioid shape. The rotation, instead of positive 90 degrees, it's going to rotate negative 90 degrees.
So you think the tip is going to be in the negative y-axis?
Yes.
Okay, that's a good guess. Let's see what happens. Very good. There you go. Actually, a reflection across the x-axis, as opposed to a rotation.
Oh.
So when you talk about rotation, you can't just compare with the sine. I'm sorry, with the cosine, rotation of cosine. We compare this with the original 1 plus sine theta, and that's going to go pointing upward. So this is actually a reflection, not a rotation.
Okay, I see.
See there? Should probably change the window a bit quicker. Let's say 5. Oh, also let me show you what happened when this is when the step is very big. Let's say step is 30 degrees. Okay. Now you're going to get a very, very jagged, but very quick drawing. So you see here, at each point that they found is 30 degrees, and then they just take that and add a straight line to it. So you're going to get something that's very jagged. Now, if I even increase that a little bit further, say 60 degrees, you're only going to see 6 points between 0 and 360, right? That's multiple of 60. You're only going to see 6 points, and that's not a very good graph. Okay, so you have an idea of what to do when you see something very funky. If your theta step is very small, like 0.01, it's going to take forever for it to draw, because it's going to find like thousands of points to plot it. So you don't want it to do that. Now, if you want it to stop, you just hit the on button, it'll stop. Okay, so let's see what happens if this is larger.
Professor, do we still characterize these shapes as a cardioid?
Yes.
Okay. And so, is there such thing as a limison for sine cardioids?
Yes. Limison just means they have a little loop inside it.
Okay.
All right, so here I just graphed 1 plus 4 sine theta. So you can see here that I'm going to go all the way up to 5. So that's a plus b. The difference here is 4 minus 1, which is 3, or b minus a. The here in this example is x-intercept at a, which is just 1, and you get the whole picture here. Okay. Now what we're going to look at is roses. Okay, so let's okay, so let's increase the n value. All right, so let's say 2 cosine of theta. Let's see what we get here. All right, what do we get? I should probably put the window back to 2. What shape is this?
The circle.
Yeah, it's a circle. Now, notice how many times does it rotate around?
2 times.
Hmm?
2 times.
Mm-hmm. Yeah, I rotate around 2 times. Now, I'm going to change one thing. We change the coefficient. Ooh. Ah. There you go. How many times does it rotate around?
4. I think 4.
No, it only repeats 1 time. Like, it doesn't go over itself. Okay? So this only is 1 time. Whereas, yeah, it doesn't go over itself more than 1 time. Okay, so now I'm only going to stop the window from 90 degree. And I want you to see what happened from 0 to 90. Right there, from 0 to 90. You see what happened? It went
It's not
from,
a complete circle?
yeah, it's not complete, but you can see what happened here. It goes from first quadrant to the third quadrant. Why is that?
Mhm.
I'd like you to look at this again. Why does it go from the first quadrant and then jump over to the third quadrant? Think about the graph of cosine of 2 theta. What is going on here? You know what that 2 inside the theta, next to the theta, do to the graph of cosine?
2 times data minus 2 times 90.
So the 2 inside the theta, next to the theta, actually compresses the graph and changes its period. Remember how we graph of sine, cosine? That 2 there tells you that you have 2 complete cycles within 2 pi. That means that the graph is being compressed, so you have 2 complete cycles. So that means that between 0 and 90 degree, you're actually going to have covering more of the graph of cosine. When you do that, the second portion of the graph, from 45 to 90 degree, the cosine value is actually negative. And that's why it's in the third quadrant. Because r is negative, you're going to push it, go in the opposite direction to go to here. Now, I'm going to change that from 90 to 180. You can see where it continues to go. And it goes to the fourth quadrant, and then to the second quadrant. And then it's going to loop back to the third, and then back to the 1. Let's look at the whole thing again. I'm really going to slow this down to theta equals 1 so you can see. So that's 45 right there. That's 90. Next 135. There you go, 180. So I need you to sketch this. I need you to sketch the path that this takes. And then I'll give you a little bit more details on how it's going. So I can show you the PowerPoint. All right, so here is the path. This we call this a rose. Now, how do we get 3? 3, or the A value here, is going to be the length of the petal. This 2 right here is going to tell you how many petals it's going to have. If this is even, you're going to double. So this is 2, so you're going to get 4 petals. If this is 4, you're going to get 8 petals. What happened when it's equal to 3? We're going to look at that in a second. Copy this down first.
Professor, I have a question looking at that graph.
Go ahead, Aim. What's your question?
I'm sorry. For the graph, it seems like they have these line drawings to limit the angle that the petals can be created in. I want to understand.
Wait. You talking about this line right here?
No, I'm talking about. Let me go to the whiteboard so I can write it as well. 1 second, please. This is what I'm curious about. I'm talking about like these lines right here.
Oh,
Is there some kind of logic to that in order to get the petals to be within those limits?
no. Those lines are just angles. That's 30 degrees, 60 degrees, and so forth. It's just help you draw.
Okay, I
Yeah,
understand. Thank you.
this is like graph paper. So instead of you having like boxes or Cartesian coordinates, that's why they call it rectangular coordinate. This is polar. So each one of these circle represent one unit. So this is 1, 2, 3. Each one of these line here represent an angle. Just like when we have the polar coordinate earlier, like this. These are the lines that they're talking about here.
Got it. And then we have these roses right here, right? Would the point right here also be -3 and +3 respectively?
Oh, okay. Well, yes. Yes and no. In Cartesian coordinate, this is -3 and 3, but we don't have a -3 and 3 per se. We only have r being positive or negative. So any point on this circle right here has an r value of +3.
Oh, yeah, okay.
But it's also depending on the angle you're talking about, where you can talk about -3.
Got it.
Okay. All right. So what do you think happened if I change this 3 to a 4? Let's go back to the calculator. Okay, so let's change this to a 3. I'm sorry, to a 4. Okay, so now at 4 give us the length of the petal, and you can still see there's 4. Okay.
Yeah.
Now, if I change this value in here to a 3, Soraya, what do you think will happen to my petals? The number of petals. Soraya?
Uh, I
Well, the
just
previous one was 2, right? And I got 4 petals. So if this is a 3, what do you think?
oh
How many petals do you think we should get?
It's 3.
Just 3. Why?
Oh, I don't
So,
know.
so here we go. So look at the path of it. Okay. So you only get 3. Look at the path. That is going over itself again. So that is the reason why you only have 3 petals, whereas if you're mistaken, that would be 6. So the reason why it's only 3 . Everybody back yet?
Yes.
Oh. Yeah, it looks like we all have a problem connecting. I ended my video. I'm recording. Oh,
Every I'm connected.
yeah, me too. I just lost connection as well. So it's something to do with the internet. Well, all of us have problem with the internet. But we're almost done.
I thought, but if the coefficient is odd number, that just makes it be perpetual, right?
Sorry, say that again.
The coefficient theta is odd number. In this case, it was 3. It just means there's that number of petals.
Yes. Yeah, that's the reason. The reason for that is because it goes over itself again. So within 0 to 360, it's actually going over itself twice. Whereas if the coefficient of theta is even, then it's going to not do that and give us double the number of petals. I think we may have to end this here because the connection is really bad. So we have a lot of time, so we can continue this. We can pick this up next week. Can you guys hear me?
Yes, I heard you.
Yes.
I mean,
Soraya? Yeah, let me. I think everything is okay now, right?
everything sounds good to me now.
Yeah. Okay. Okay. Let's continue then. Okay. So we can wrap this up in a second here. All right. Let's look at what a lemniscate is. Okay. A lemniscate. So basically, this is the square root of plus or minus. So we're going to look at what happened when we just only have cosine of 2 theta, but this time we're going to take the square root of it, and anytime we take the square root, we're going to have plus or minus.
Professor, I've lost video. Did anyone else lose video?
Oh, I'm still seeing video for me.
I can see anything, just the dark,
Black screen.
yeah, black screen.
Oh, okay.
Yeah. Let me try to re-enter the Blackboard.
Go ahead and try refresh.
Hello, can you hear me?
I can still hear you.
Yeah, so I just guess the screen is still black, so you're not sharing any content.
Hmm.
I think this is the Blackboard server issue.
Yeah, I don't think this is going to work. You guys are not hearing me, and you're very choppy right now. Okay, so let's continue this next week because
It doesn't work, I think.
yeah, it's not. I can barely hear you, Soraya. You're so choppy. So let's call it a day here and just pick it up next week. We're ahead, so I'm not too concerned. All right, see you guys.
Bye.
Bye.
Bye.